Dear participants, welcome to the last session of Day 3 Room 1 presentations. In this session, we are hosting 4 very valuable scientists. Our first guest is a Nobel laureate, Dr. Asari from Qatar. Professor Dr. ERDIN BOZKURT from the Middle East Technical University, Turkey, is our second guest. Then, Professor AHMED KETTAB from the University of Boira, Algeria. And lastly, Professor SALIM ETSOURI from Algeria. Welcome, professors. Firstly, I would like to invite the Nobel laureate, Dr. Asari from Qatar. Dr. Asari has been awarded with the Nobel Peace Prize in 2007 as a member of the IPCC working group. We are looking forward to hearing your presentation, sir. The stage is yours.
Thank you very much. Again, my regards to everybody there, and I wish if I was there in person to deliver this presentation, because you have a beautiful country, and it's always a pleasure to be there. Today we were going to talk about converting natural gas into animal feed protein, and you know, this is a situation. This is the situation which has been very necessary as a result of what is happening worldwide with regard to climate change, and the situation here in Qatar being, you know, that the economy is basically based on fossil fuel exports and all this. And we have been trying here in Qatar a number of ways in order to go along with the situation where the world economy would have to go into zero carbon emissions by the middle of the century. And we have, of course, a number of portfolio of mitigation measures covering the fuel efficiency measures in order to reduce the emission of carbon dioxide and greenhouse gas emission in general. We also involved in carbon capture and storage, also as a way of removing carbon dioxide emissions from the atmosphere. And very importantly, also, we have a lot of work here being done on renewable energy, particularly solar energy. And with regard to the transport sector, also there's a lot of work here in electrification of the transportation sector, and measures also in the building and construction industry, also to limit the emissions. Despite all this, as we all know, that pressure is really mounting to diversify the economy away from the energy completely. The primary source of emissions and the primary source of climate change. As you may probably know, Qatar is completely committed to the work of the NFCCC, and actually this is a testimony to this, the nationally determined contribution under the Paris Agreement, which is actually at this particular time, people are discussing, you know, how to implement the Paris Agreement and the commitments by the countries and all this. Qatar has committed itself to 25% greenhouse gas emission reduction by 2030 relative to business as usual emission scenario. Of course, there is a number of ways, you know, to protect the environment and at the same time continue sustainable development, and without, you know, jeopardizing, you know, the economy of the country and the welfare. And in this particular direction, we are also exploring the potential for converting natural gas into animal feed protein. Animal feed protein using natural bacteria and biotechnology developed in Denmark as an approach for economic diversification with emission mitigation co-benefits, and also as a route for food security, because as you understand, animal feed is very important, for the poultry industry and for the husbandry and so on. So we are going to talk about, the suitability of the single cell protein produced as a result of synthesis by natural bacteria using natural gas, and we will also look mainly at the environmental, benefits of this. And now here, I think we have a slide here showing how the natural bacteria, which is called Methylococcus capsulatus, natural bacteria, how it require only the methane in the natural gas, and then we have to add oxygen and nitrogen and minerals. And overall, this it's fermented in a U-tube reactor, which we will talk about in the next slide, I suppose. But generally, the protein that is produced as a result of synthesis by this natural bacteria is really excellent. It contains crude proteins about 70%. And it contains lipid 10% and the fiber 1%, carbohydrates is almost about 12, and the mineral 7. It's free of toxins, dioxins, heavy metals due to controlled production process. Here, actually, we're talking about this pioneering company. We call it Gulf Biotech Plant. The company has already secured the permit to go into this direction to produce animal feed protein, or SCP, single cell protein. And the fermenting bioreactor, I will talk about it later. And the key input are the natural gas, oxygen, water, and minerals. They create the environment for the bacterial growth. And the natural bacteria renders the natural gas into unicellular protein. Its amino acid profile is well in line with fish meal, nutritionally favorable, has high content of methionine and lysine. These are critical amino acids for protein development. Here, this is a very complicated picture of the process diagram, and we are allowed to see this because the company in Denmark has already developed this, and as you can see, the heart of the process is a U-loop bioreactor, I think shown in the right, and it is on the left of the big diagram. And you can see that the solution of water and phosphorus and minerals, and including magnesium, iron, and all these minerals which are necessary are added to the fermenter, and phosphate also supplied as phosphoric acid and other minerals requirements. So this is the recipe which enters into the bioreactor, and then pure oxygen is used for oxygenation, the fermentation process, and then the gases are introduced to the left of the loop, and so on. And in the U loop, that's where all the the synthesis by the bacteria occurs, and from there it goes into biomass, continuously harvested from the U loop fermenter, and eventually water is separated in the next stage, and then I think it is added back into the U loop, and then we go after the biomass is separated, is homogenized, and then it goes into a spray dryer, and from there we have the product, which is collected and kept in silos. I don't really want to go too much on this, because this is the heart of the heart of the process, the biotechnological aspects of it, and there's a lot in it. And I think this is also another aspect I elaborated a bit, because this is where the spray dryer, because it emits, because it has to it run on either electric or perhaps fossil fuel, and we needed to know how much this part of the process. So it operates at 45 degrees centigrade. Of course, it has a cyclone to remove the particles and the bag filters before the exhaust air is out. Bacterial biomass concentrated to 30 dm by centrifugium. So it has a lot of water, and the concentrated biomass would have to be heated to 140 for sterilization, then cooled to minus 70 degrees to 70 degrees centigrade. Finally, it is dried with an integrated fluid bed, giving a non-dusty product. It actually it's a very attractive product, because it looks like it's not dusty. It is I don't know what's the word for al-ajwa. You don't know that one. So the key element is the U-loop fermenter and the cyclone driver. It's the dryer, and then you have the product. Okay, I think now we're getting into more numbers, and as you can, I'm not going to take too much time on this, but as you can see here, this is the profile of the product. So the product contains over 70% crude protein, about 10% crude fat, and then you have the crude cellulose, and you have ash, and you have natrium-free extract about 11.8, and the nucleic acid. And actually, the nucleic acid is an issue, because this is one of the materials the company is working on. We're doing research to reduce the nucleic acid, because when consumed by larger mammals like a human being, nucleic acid, because it's a little bit high, 4.8% for the ribonucleic acid, and 2.4% for the deoxyribonucleic acid. This one, I think, it creates stones. If it's stones in the kidney stones, if it is consumed by human beings. And the company insists that this protein is good enough even for human consumption, provided this nucleic acid is reduced. And as we are really communicating with the researchers in Denmark, they said that they have now actually reduced the nucleic acid to 1%. And 1% is good enough. That makes the product perhaps suitable for human consumption. And you have the amino acids there. It has all the amino acids necessary for for consumption, and the vitamins, and also the fatty acids, and the relative distribution in the extract are shown there. And a very important issue here is that this material or this animal feed has been actually approved by the European Union Commission. So it is now being used in Europe, and I think there is a big factory in Denmark, And as I understand that the same researchers, I think they have now have a joint venture with in Russia, where they also have a large, factory for this. Also, this novel approach is being conducted at the same time in California. This way, we go to the second one. What are the benefits of this this novel approach? I think it's very important to understand that this material, this product, it relieves the pressure on arable land, while it takes 1 hectare to produce 700 kilograms of soy for 700 kilograms for 1 hectare. The same hectare will produce 25,000 tons of SCP. Regarding the greenhouse gas emission, and I will talk about this later on in detail, our calculation, which I have made, it shows that carbon dioxide emission, equivalent GHG emission, is less by 50% compared to emission resulting had this gas was used for energy. So we have a 50% reduction in carbon dioxide. We also, the process uses less water. Only 5 liters are needed to manufacture SCP protein compared to 600 liters of water required to grow 1 kilogram of soybean. So you can see the difference. And the effluent characteristics, less liquid, waste, or sewage discharge into a river or to the sea. So the effluent characteristics are good enough that it can be dumped without any treatment. Essential to the state of Qatar, it is essential because there is an expansion in the poultry and animal farming in the country, in line, and it is in line with the national security program of Qatar, because as you understand, Qatar doesn't have, agriculture is very difficult here because of the weather and because of the desert situation, all this. We'll go to the other one. Okay. Now here, what we did here, I did the calculation, which I do very well. The calculation here, we based all these calculations on a base capacity, only 6,250 tons per year. So if we want to produce 6,250 tons, this is the prototype. And then we did the calculation based on that. And you can see here what will be requirement. The requirement will be, to produce that much, we will need the gas use. And somebody is calling me from your side. And you can see, how much of the material the electricity used per ton, the natural gas feed. We calculated how much we will need, and the feedstock water, and so on. And then we looked at the biomass empirical formula, which is on the right side of the slide, and using that. We developed this, the equation, the biomass synthesis equation, and based on this, then we did the calculation for how much we expect in terms of emissions and all this. One a very interesting issue here that, as you can see, that if you have 1 mole of methane, you will need that much 1.45 oxygen. And then you'll have, you need ammonia, 0.108, and the biosynthesis of the bacteria results actually in carbon emission because of the fermentation reaction. Based on the above and the process data shown before, so the provisional emissions were calculated, and I don't want to get you in all these calculations, but I want to tell you that for the base case, we will have water emission from the reaction itself will produce 14,375 meter cubes or tons, and the electricity calculation, we know how much will be needed for the electricity, and we know how much if we use the total carbon emission is 13,000 tons. And I think there is a 10,000 tons there. I cannot see it here. That comes from the reaction itself. So the total, I don't know why the 10 is not there, but I think there is a 10 tons. Yes, it is there. The potential annual GHG emission from the use of the natural gas is 625 times 1.6 ton, which is when you calculate it, knowing the molecular weight, carbon dioxide, it turned out to be about 10,000 tons. 10,000 tons, it is not in bold, that's why I couldn't see it. And you have another 14,000 coming, that's water, but you have 3,620 tons. This is from the spray dryer. And so you really, the process will do about 13,630 tons. Now, if you use the same amount of gas to power, say, a turbine, or you use it as a fuel source, the equivalent emissions will be not less than almost 24,000 tons. So, judging by this, we feel that the reduction resulting from utilization of converting the natural gas into feed protein will save the environment of almost 50% of the carbon dioxide. I will show later on that the process itself, resulting in emission from the. If we go back to this one. Yeah, the degassing unit. If you say in the bioreactor, there is a degassing unit on the top, and it mainly emits carbon dioxide, if you can see there, and but it also a number of the reaction material itself, with the methane and other hydrocarbons, C2 and the C3 and all this, they also come out from the gassing unit. And later on, I will show that this amount actually the company is saying they are not going to vent it in the atmosphere, they are going to capture it and recycle it. And so that will mean, and we calculated that amount is more than what the spray dryer will need. So that means even the 3,060 tons resulting from the 3,600 resulting 3,600 tons of CO2 from the spray dryer, if you use electricity, will not be needed if we are going to utilize it as an energy source, and we calculated that it is more than enough to run the dryer. So if that is done, that will mean that the only emission will probably be only 10,000 tons in comparison to the 23,000 tons, and that will mean that the saving is actually more than 50%. I think it is mentioned here, the primary emission from the degassing unit on top of the U-loop, fermented and nitrogen gas, oxygen, CO2, and methane. Emission estimates have been calculated per hour and annually. The annual flow rate, and this is calculation ought to harmonize with the based on renewable current data, emission of methane and ethane totaling 1,486 tons per year from the degassing unit will not be vented. It will be captured and used to fuel the spray dryer. That means the annual fuel requirement for the spray dryer, we calculated it, and I think we reached from that what is vented is more than what is needed by the spray dryer, and that will mean that the process is going to save more of the CO2 emission that otherwise would have come out from the degassing unit. I think this is here we made a comparison of the spray dryer, whether it is the initial national commitment, the spray drying technology. I think what the comparison is made here between the emission from as a result of using the spray dryer in comparison to the emission we know here in Qatar. And as you can see at the very end of the table, actually the percent is very, very low. It's actually compared to the total emission, CO2 will only be about 0.006%. NOx is trivial. I think the emissions are very small had we used the spray dryer and we use fossil fuel to run them. This is all about this. I don't think there's much in it. But anyway, all this emission will be saved as long as we are using, we are recycling the emitted hydrocarbons into the spray drying, because the spray drying is the only source which might probably cause extra emissions. So as you can see here, because we wanted to show that the emissions are very small, and as you can see there, emission of CO2, modified Qatar national annual emission is only it is on the right side of the table, and it is in the kilograms per year and all this, the NOx and the NOx. This is all from the spray dryer, and we did this because the regulator here, where I work now here, fortunately, the regulator were very specific about knowing how much, this process, this is so-called sustainable development process, how much damage it will do to the environment, and that's why we went all the way to go into all these calculations, showing that this is very trivial. So the project has negligible impact on ambient air quality at the project site and does not require further scrutiny. Had a full EIA investigation, including modeling, all has to be done. I think here, this table also with all this, a lot of numbers, I think it can be summarized. If you can see the very right hand, the last column on the right, it talks about how much of the characteristic of the effluent, because this thing is done in solution and all this. So I did a calculation for all these, what will be the product, and what will remain in the material, and what will go into solution, and what will be part of the effluent, because it's very important to know what this process is going to do to the environment, whether it is the atmosphere, not only the atmosphere, but also what will be what will do to the water environment, the receiving water environment. So the calculation I did really showed that the process is very efficient. Almost about 100% of the material that goes into it is used very efficiently. There's some calculation here showing how much moles of ammonia and all this, and 62% of the natural remains in solution is recycled back. It's recycled back. I think this is one of the issues, the nitrogen content, but it is recycled back in the U-loop fermenter. So, and 85% of the ammonia and 75% of the phosphorus and almost 90% of the magnesium sulfate. These are the elements which would have to be in the feedstock. All these micronutrients are assimilated in the uniprotein product. So there is very little it goes into the effluent. And the potential emissions are very minimal. Regarding solid waste, there is no solid waste that generated from this normal operation. If it's operated normally, nothing. Current estimate of solid waste generated from spray dry and cyclone battery stream is below 0.01% of the total annual product, which is very little. And 75% and 89% of the magnesium sulfates and all micronutrients are assimilated in the product. So the remaining matter in solution is relatively negligible, and the fraction of processed liquid that is recycled back into the ULF, the U-loop fermenter afterwards, is separated in the process centrifuge unit and prior to drying. So most of this liquid, they go back into the fermentation reactor. And because of that, as you can see here on the right hand side, very little coming out. I think you have, for instance, the ammonia is almost about 3 grams, 3,000 ppm, and the magnesium is very small. I think it is a very efficient process. And in conclusion, this single protein material produced by biotechnology from natural gas and natural bacteria is a novel animal feed, and it is certified by the EU directive. The product contains all essential proteins, amino acids, minerals, and vitamins, and is not genetically manipulated or containing toxins. It is suitable for animal feed, for fish, poultry, and animals, large animals, and has long shelf life and can replace soybean meal and fish meal. The product relieves the pressure on arable land, water resources, and the farming and fishing industry. Greenhouse gas emission from this industry, is about at least 50%. But if we add the saving from the spray dryer, this 50% will probably go to about 70% compared to combustion emission if we use the natural gas as energy use. The process is essential to Qatar in two ways. First, as a viable option for economic diversification away from the energy sector. And second, it secures animal feed protein to satisfy the expanding demand for animal feed protein needed by the poultry, animal farming, and the aquaculture industries. I thank you very much for listening to me, and I hope I wasn't boring. Thank you.
Not at all, Dr. Asari. Thank you very much for sharing your valuable research with us. Our next guest is a very valuable, respected professor from the Middle East Technical University, Professor Dr. ERDIN BOZKURT. Thank you very much for showing the courtesy of being with us, Professor. We are looking forward to hearing your valuable research. The stage is yours.
Well, can you see my slides? Yes, you can now. Okay, well, I will be talking about structural controls on geothermal plate. This is going to be a purely earth science presentation. At the beginning of my presentation, I would like to show my deepest respect to our hero, great leader, Mustafa Kemal Ataturk, because today we commemorate the 83rd anniversary of the passing of Mustafa Kemal Ataturk. I would like to share one of his proverbs. He basically says that to see me doesn't necessarily mean to see my face, but to understand my ideals, actually. Well, if we look at the recent developments in the energy world, there is an increasing demand to energy. The global fossil energy prices are very high. And we also know that these fossil resources have negative effect on climate. And basically, all of these issues necessitate the use of environmentally friendly and suitable green energy resources for both electricity generation and the heat. Well, in this regard, there are many developments worldwide, but when we come to Turkey, we see that in this way, geothermal energy has played a dominant role because Turkey, especially Western Turkey, have its very rich geothermal potential. And to date, in Turkey, we have more than 60 power plants. The installed power has been increasing over the years. Annual electricity production in that regard increases, and the ratio of production to consumption also increases. So it has a very dominant role in Turkey. Well, this means understanding of the geothermal systems in Turkey is crucial. So in my talk, I would like to just present some of the results of our recent research in the area. So what I'm going to do is to introduce geothermal systems for those who are not familiar what geothermal system is, how it operates. I will talk about main elements of geothermal systems. Then I will basically mention about the factors that controls geothermal systems. And after that, I will move to Western Turkey and provide you some of the results of our research. When we say geothermal research, actually we mean convecting water in the uppermost part of the earth. This is basically a confined world where the heat is being transformed from the deeper sources to the surface usually. And when we examine the geothermal systems, we see mainly three elements: heat source, a reservoir which keeps the fluid in it, and we need a fluid which carries and transfers the heat from the deeper parts of the earth to the surface. So the source of heat is a big question actually, and it varies from one region to another. We have mainly two main sources of heat. One of them is coming from the very shallow intrusions, magmatic intrusions. They are very shallow, they are very hot, and the heat released from these intrusions are more than enough to heat the fluids around. And the second one is basically geothermal gradient. We know that normal geothermal gradient is about 30 degrees centigrade per kilometer, but there are some particular locations on Earth where the geothermal gradient is very high. Western Turkey is one of those areas in the world. We name these systems as amagmatic systems, and in this case, faults play a major role in the transfer of fluids, as I will be describing in a minute. Well, of course, depending on the heat, these geothermal systems are basically named as low enthalpy, intermediate, and high enthalpy resources. And the figures about the description of those resources varies from one school to another. In this slide, I just want to show you the fact that how it is variable from one author to the other about the description and definition of the low, intermediate, and high enthalpies. The second important element of geothermal systems is a reservoir. We are actually talking about a hot, porous, and permeable rocks, which allows the circulation of those hot fluids. And these reservoirs are usually connected to the surface because this is the only way they get replenished. And usually, to keep the system safe, I will say, we have an impermeable rock above this reservoir rock. This basically keeps the reservoir in a kind of safe position and keep the reservoir working. Of course, there are different types of rocks which works as a reservoir. In many cases, limestones or their metamorphosed equivalents, marbles play very major role, as it is the case in Western Turkey. The geothermal fluid is usually the meteoric water which originates from the surface. The water is either in the liquid or vapor phase, depending on the temperature and pressure of the environment, and it usually carries some of those gases like carbon dioxide, hydrogen, sulfur, and some of the other gases. Well, the mechanism of this geothermal system varies from one region to, depending on the source of heat and depending on the geology of the region. But geothermal systems in extensional terrains worldwide, like the case of Western Turkey, normal faults play a major role in the formation, in the evolution and control of the geothermal activity. So faults are really very, very important. The mechanism is what we call fluid convection. Okay, the reason is very simple. The fluid gets heated up, and as a result, there is what we call thermal expansion of the fluids. In the presence of gravity, basically, heat drives the flow of the hot material along the faults. So faults basically play the role of conduit along which the heated fluid, which has a lower density relatively speaking, tends to rise, and basically as it rises towards the Earth's surface, it mixes with the cooler water and becomes denser materials and basically concentrate along the geothermal margins. In some cases, the meteoric water uses these structures to come to the deeper parts of the Earth where the temperatures are very high, and basically this hot water tries to rise to the surface. Either it's being kept within the reservoir rocks or it's been basically following its path to reach to the surface. In these systems, as I say, faults play a major role. The meteoric water infiltrates down along these faults, goes towards the deeper parts of the Earth, and reaches to what we call reservoir rocks, which is porous and permeable. There it gets heated up. Then it will be moving from the reservoirs into the fault zones where it is trying to rise towards the Earth's surface. In some cases, it reaches to the surface as hot springs. In other cases, it has been kept within the reservoir, forms what we know hidden geothermal systems. Of course, as I say, faults play a very important role. When we look at the literature, we see that there are different structural settings which are favorable for geothermal systems. One of them is what we call as the horsetails of the faults. Major faults basically splay out into smaller segments, and these segments are usually considered as one of the key localities to localize geothermal systems. In other cases, we have major normal faults. These major normal faults overlap. The overlap areas have local stress anomalies where we have what we call relay ramp forms. These relay ramps basically are dissected into several fragments along major faults. This will basically stimulate porosity and permeability, which is known as secondary porosity, secondary permeability, and these areas become suitable for geothermal systems. The other way is the areas where major faults intersect. These intersection areas are key localities for the geothermal system formation. And again, intersection and termination of major faults will be considered as the main areas or sites for geothermal systems. In some cases, strike slip faults, as I say, splay out into smaller segments where they form closely spaced extensional faults, and these faults will become site for geothermal systems. And again, in association with the strike slip faults, overlapping areas, pull-apart basin formation, dissection of the pull-apart areas, again suitable for geothermal systems. The others are associated with the magmatic activity, and they are mainly considered as the magmatic systems. There again, faults play an important role, but the caldera margins are key features or tips of the dikes. We don't see this kind of features in Turkey very much, maybe in Eastern Turkey, but mainly we see geothermal systems in association with the faults. And when you look at the regional examples of those geothermal systems which are associated with the faults, we see that major normal faults accommodate about 5% of the geothermal systems. But these three items are very important. Step over or relay ramp areas in normal faults, about 32%. Tip of the normal faults, about 22%. Fault intersections are about 22%. So you see that normal faults and interaction and intersection of these normal faults play a very important role in determining and controlling the geothermal system formation. This means understanding of the faults and fault systems are crucial in the geothermal exploration. Well, you may have a simple question, why faults are important? Here is the very simple answer. Faults are usually associated with what we call damage zones. Almost all of the faults have these damage zones in association with them. These damage zone areas are the areas where we have stress concentration, okay, which is most common in areas at the tips of the faults, along the fault systems, or at areas where faults basically interact. And we know that there are three types of faults. One of them is the tip of faults, as the name implies, they occur at the tip of the faults. The other one is wall damage zones, which occurs all along the fault strike. And the third one is maybe the most important one, is the linking damage faults, where faults basically overlap, interact. And this means these areas are key localities for the geothermal exploration. And we know that the formation of these basically damage zones are associated with the initiation, propagation, and interaction of the faults themselves. When we say fault tip damage zones, we are basically talking about stress concentration, extensive fracturing along the tips of the faults. And when we say fault damage zones, we are basically talking about similar stress field, intense fracturing along the walls of the fault themselves. So these damage zones are really very important, because we know that faults basically play the role of conduits. What happens actually, the heated hot fluid uses these damage zones to make their way to reach the surface, and as they move up along these damage zones, they become cooler and cooler. Eventually, they will localize in reservoir rocks. So better understanding of these damage zones are really crucial. So what we have in these damage zones? First of all, in these damage zones, there is extensive and intense fracturing. This means clustering of many small-scale faults and fractures. This means increase in porosity and increase in permeability, which is known as secondary porosity and secondary permeability. This means because we have porous medium and permeable medium, the fluids can easily migrate and accumulate. So the damage zones therefore becomes sites for the migration and accumulation of hydrothermal fluids that we know them as geothermal fluids. Of course, we know that these damage zones are distributed all over the faults where we have brittle deformation. So intense fracturing, then permeability. These areas, damage areas, therefore forms suitable fractured reservoirs, which will be the target for the exploration. That is why these areas, damage zones, becomes the target for geothermal exploration, target for borehole drilling. Of course, the presence of faults does not mean always you have the target, because we know that these faults usually form systems, fault zones, where we have several faults being parallel or subparallel to each other. So the exploration must address which of these many faults in a given region will be the suitable location for fluid percolation and fluid basically nesting. That is why geothermal exploration, the methods you apply during this exploration, plays a very important role. In this case, you have to have a well-organized and professional, careful approach. You have to choose the best exploration methods the methods you apply should have a kind of tailor-made approach with respect to the concession area, and this may vary from one prospect to another. You have to develop the best suitable exploration strategy. This strategy must have a stepwise approach, and this strategy has to be revised as new evidence coming into the picture. And eventually, you have to integrate the data coming from the field-based studies, the data coming from the geophysical studies, and the data coming from the borehole studies. So as a result, you are to characterize the potential reservoir, which is basically hosting the hot fluids you are after. And this characterization will be very useful, especially for you to hunt blind or hidden geothermal reservoirs, which has no surface expression. And eventually you need to develop a 3D conceptual model from which you will basically decide favorable drilling sites. Please note that the cost of single well bore is more than the money you spend for the exploration. So the best and tailor-made exploration strategy is highly required to have your target and to basically hit the bullseye. So what you have to do in this case, you have to do a proper geological mapping, geological data. You have to have geophysical data obtained from which you will basically provide a 3D geological map. Using the information available, you have to have fault stress analysis. You have to have basically a study where fault intersection and termination density is being modeled. You need to understand the suitable stratigraphic intervals, lithologies for a possible reservoir, from which you will basically develop a 3D geothermal potential. Then you will develop a 3D conception model. I will basically repeat the same issue without doing all these steps. If you start drilling your target area, this may be a nightmare for you, and you will spend money for nothing really. So what I will do, I will basically present some of our results, which basically accompanies all of those steps in Western Turkey. For those who are not familiar with the geology and active tectonics of Turkey, let me summarize what are the major structures. Well, we have three major strike slip faults. One of them is the North Anatolian Fault Zone. It runs all the way from the Northern Aegean Sea, from Gulf of Saros through Sea of Marmara region, all the way it cut across Anatolia and basically trends till what is known as Karlova. This is a right lateral strike slip fault. We have a left lateral strike slip fault, which is known as East Anatolian Fault Zone, and it's running through this portion of the Anatolia. We have third fault, which is known as Dead Sea Fault. Anatolia between North Anatolian and East Anatolian Fault Zone escapes westward, okay? And in the west, in relation to this westward escape and subduction processes in the Mediterranean Sea, we have north-south extensional tectonics, where most of the geothermal sites are located. So I will basically concentrate to this region for your better understanding. Western Turkey in this regard is known as non-magmatic, fault-controlled, intermediate to high enthalpy geothermal systems. In these systems, normal faults or fault zones play a very important role, so better understanding of fault geometry, interaction and intersection of these normal faults, and the final structural pattern devised by these normal faults are important because they control the formation and localization of the geothermal systems. That is why better understanding of the fault geometry and structural pattern in a given concession area is highly desired. In Western Turkey, we have mainly three major structures. One of them is low-angle normal faults. These are the faults which are basically responsible for the exhumation of the lower middle crustal rocks of the Menderes Massif. There are three of them. One of them is in the north, known as Simav detachment. The second one is Gediz detachment, which lies along the western margin of Gediz Graben. We have the third one, Büyük Menderes detachment along the northern margin of Büyük Menderes Graben. And we have a fourth feature, which is known as a ductile shear zone to the south, and we name it as Southern Menderes Shear Zone. And if you look at this area, we know that the region is dissected by several approximately east-west trending grabens, and all the grabens, as this diagram illustrates, is basically controlled by the high angle normal faults. Some of these grabens are from the north, as the Edremit Bay. We have Bergama Graben, Gediz Graben, Küçük Menderes Graben, Büyük Menderes Graben, and Gökova Bay to the south. I will mainly concentrate on the Gediz Graben and Büyük Menderes Graben because these are the most significant structures of the region, and these are the grabens where we have most of the geothermal systems to localize. When we examine Western Turkey as a major feature, we see that large-scale faults represents the first-order structural control on the geothermal systems. They are used as conduits and control the fluid circulation. The damage zones along these faults play a permeable medium so that they bring the hot fluids from the deeper parts of the crust. So they basically are responsible for the induction of intense geothermal activity in different parts of the earth. So we see them as many springs all around the region. So this means there is a close correlation between geothermal systems, hot springs, and the location of faults, especially location and intersection of faults. I would like to whet your appetite with some of those views from these major structures. This is the view from the southern margin of the Gediz Graben, where you see this detachment fault. You can follow it for several kilometers along strike and several kilometers along dip. These are the metamorphic rocks of the Menderes Massif. These are the Miocene sediments which are accumulated in the spread detachment basin. And here you see the graben itself, and these are the high angle normal faults which dissect the area. This is another view of the detachment fault, a beautiful surface. In some cases, the dip of the fault is around 20s or less than 20s. In other cases, you may see these faults as horizontal structure, I will say. This is another view from the fault itself. Immediately we have cataclastic rocks, and above dipping, these are the bedding planes of the Miocene sediments. The detachment faults are dissected by high-angle normal faults. This is one of those high-angle normal faults, which forms the boundary between metamorphics of the Menderes Massif and Miocene continental sediments. Some of the faults I will be showing are basically located within the Myo-Paleocene sediments. This is from Turgutlu area. This is another view from the Turgutlu area. As you can see, juxtaposition of different lithologies of the continental sediments are very clear for our observation. In some cases, these high-angle faults display beautiful fault planes. This is from the Muğla fault. This is from the Manisa fault. And this view is also from the Manisa fault. They have pristine, final fault planes, beautiful fault planes. You see every geological feature that may form along the normal faults on these fault surfaces. Of course, the faults are very extensive in the region. I just would like to show you one of those areas where intense faulting and fracturing is really very effective. And all these faults are used as pathways for the fluids to circulate through from the deeper parts of the earth towards the surface. Apart from these structures, there are also north-south structural faults which both dissect the detachment faults and basically compartmentalize the inner structure of the grabens. Well, some of those major faults is being mapped by myself and my student, and we basically know that grabens are very much dissected and subdivided into subgrabens, and this is a view from the Gediz Graben, where we have three distinct sub basins which are basically dissected by these east to north-south trending strike-slip faults. Actually, the density of these faults are more than you can think of. This is a map from Öner and Dilek, again from the southern margin of the Gediz Graben, and you can see that the graben and the detachment fault is dissected by many of these strike slip faults. This means strike slip faults, detachment fault, low angle normal fault, high angle normal faults play a very important role in localizing the geothermal systems. This means better understanding of this structure is crucial for the geothermal exploration. So these are the areas that we have worked to explore these relationships. We have used surface geology, we have geophysics data, mainly magnetotelluric data, and where available, we also use borehole data to understand how these structures intersect, interact to form geothermal systems. I would like you to take to this part of the Gettysgraben and basically talk about two regions on the northern margin and southern margin of the Büyük Menderes Graben, starting from the northern margin. Well, this is the surface mapping. We have beautiful high angle normal faults that forms the basically grabens, okay? Then we also have basically some strike slip faults, which are basically mapped in the area. And we have sediments deposited in the hanging wall of the detachment fault. Here you see the detachment fault in general. Of course, we have many strike slip faults in the region, and they are really very characteristic. Of course, this is what we see in the field at the shoulders of the graben. What about within the graben? How we see especially these normal faults and these strike slip faults. So we have done MT campaign, and I will just share some of the results of this MT campaign. By the way, this map belongs to Orkun Global Mühendislik. I was involved in mapping of this area as well, but it is partly my work and partly their work. So what we have done, we basically carry out an MT campaign. This is one of the horizon maps you see. You can see that there are low resistivity areas. And when you just look at the distribution of both low and high resistivity areas, they really mean something from the structural point of view. If you combine this data with the surface data, and if you basically calibrate geophysical data with the surface data, you can easily make an interpretation of the horizon maps. This is one of those interpretations. I have just put only strike slip faults. The red lines represent strike slip faults being mapped in the field. Only this pinkish one is the one that has been mapped from the MT data. We have interpreted several cross-sections of the MT data. These are north-south cross-sections to see how effective normal faulting in the area. And you can see the distribution of low resistivity areas is being dissected and even displaced by these normal faults. We used east-west sections to understand the location and distribution of the strike slip faults. And you can see that the distribution of low resistivity areas define graben and horse-like structures within the graben itself. That means these strike slip faults are really very effective. Look at these areas. You can see these beautiful displacements which occurs along almost vertical strike slip faults. The MT data basically justify what we see in the field and highlights the fact that strike slip faults, which are not possible to see in the field, are common structures within the graben. When you combine all of this data, surface mapping, MT data, this is what you end up with. And you see that clearly with the distribution of the low resistivity areas. The graben, internal structure of the graben is being compartmentalized along these north-south or northeast trending strike slip faults. And some of these compartments become very suitable for geothermal targets. Some of them are not. So that means these compartments defined by the strike slip faults play an important role for fluid circulation and for basically localization of the grabens. Let's move to the southern margin of the graben, where we have done again a detailed surface mapping, which has yielded that normal faults and strike slip faults are the common structural elements, and the area is highly dissected by the normal faults and strike slip faults. As you can see, within the graben, it is difficult to trace both the normal faults and the strike slip faults, so we have another MT campaign to see those features. This is what we have basically as the horizon map. So we have several horizon maps belonging to different levels. we interpret these horizon maps. As you can see, we can see the continuation of some of those strike slip faults in the graben. We were not able to follow some of those faults in the graben, but you see that there are some major structures which dissect the graben along and basically compartmentalize the internal part of the graben. So this is what you have, another horizon map. Finally, we combine surface and geophysical data using some of those north-south cross sections. Look at these displacement along normal faults. They are really beautiful, and you can easily see that the geophysical data is really very useful to understand the structures of the graben where there is no surface manifestation. These are the sections for the strike slip faults, and again, distribution of both low and high resistivity areas are easily used to locate strike slip faults. You see different lines as black or red. These are possible interpretation of the faults. You may have really steep faults or relatively gentle faults, but nevertheless, they signifies that these faults are strike slip faults, and they have some amount of dip slip displacement as well. This is the final map that has been basically interpreted from both surface mapping and from geophysical data. And again, you see that highlight dissection by normal faults, and these normal faults are actually cut and displaced, or the motion along the normal faults are transformed by these strike slip faults, which has some amount of normal displacement. So you can see that there are grabens and holes within the east-west trending grabens. So once you have this interpretation, you again see beautiful compartments. Some of these compartments become target for your exploration. And this is the cross-section which has been interpreted from borehole data of two well bores, which has been basically drilled on either side of these faults. And you can see that the distribution of the different lithologies clearly indicates the presence of strike slip faults in the graben system, because this geometry, which is very steep with dip angle changes or dip direction changes, okay, along the dip of the fault, is very crucial and interesting evidence for strike slip faults. Of course, we have other borehole data from the region, from all over this part of the graben. So what I'm going to do is to show a kind of section across here, which has been basically interpreted from the boreholes. And when you use these boreholes, you see that, let me go back to in this area, this is right in the heart of the graben, we have beautiful graben structure, which has been controlled by north-south trending strike slip faults. These grabens and horse structures is very characteristic. Okay, this time I will take you to the north to Geddes graben, where we have done some field mapping and geophysical exploration. So I will take you to this area, okay, the area between Alaşehir to the west and Sarıgöl to the east. This is the geological map of the area, where we have mapped different lithologies and geological structures. As you can see, high angle normal faults are very characteristic features of both northern and southern margins of the graben, but there are also beautiful strike slip faults which dissects this shoulder of graben. The green lines basically shows the interpretation of these grabens. This is a kind of wishful thinking, basically highlighting the fact that these faults may basically extend into the graben, where they are buried beneath the alluvial sediments of the graben. So we have done a kind of geophysical campaign in this area, and these are some of the results of this campaign. Here you see a horizon map at a depth of 4,000 meters. These are the low resistivity areas. When you make the interpretation of it, you may basically interpret that there is a kind of strike slip fault in here. And this is how we interpret this feature. You see there are strike slip faults with some amount of normal displacement. Okay, and again, you can talk about compartmentalization of the graben in this area. This is another horizon, which is around 3,000 meters. You can see that the low resistivity area becomes very characteristic, very extensive, but still you see the same normal fault where this is being displaced. This is the interpretation of that structure. We still have the same fault, same faults, similar compartmentalization at this level itself. When you look at a section across this area, you can see that strike slip faults are characteristic, and they define a kind of horsed area where you have basically low resistivity. This could be the target for your future exploration anyway. When you make all these data combined into one, this is what you see. Again, compartmentalization of this part of the graben, where you have different compartments, okay, a kind of horse developed within the graben, and simply you can see that some of those areas become target for exploration. I take you to this area. This is right in the heart of the graben. You see nothing on the surface, simply because of the thick alluvial sedimentation, but at the same time because of the extensive agricultural activity. So the only data you can obtain from here is gonna be from the MT data. So this is what you have as an MT data. We have interpreted some of the horizon maps. Again, you have these beautiful strike slip faults being interpreted. You look at the cross sections, and you can see the either you see isolated low resistivity areas within graben or horse-like structures. Even you can see the displacement of these low resistivity areas along these strike slip faults. And sometimes you see that some of these strike slip faults are buried beneath the sediments as well. So when you make the interpretation of it, you see that in this small area there are strike slip faults which compartmentalize the graben, and there are high angle graben bounding normal faults as well. This time I will take you to the eastern margin of Büyük Menderes graben and talk about the geology and borehole data. This time we have no geophysical data. We basically produce a very detailed map of this area. I'm not going to show this one to you, but I will basically show a number of sections, cross sections, which has been basically interpreted from only borehole data and also surface geological mapping in the region. So this is what you have. This is a north-south, approximate north-south section. This basically illustrates the normal faults. You can see that we have normal faults mapped from the field data, and these are the faults which are interpreted from the borehole data. You can see that there is a really beautiful, basically step wise structure that has been devised by the normal faults. This is the marble, okay, in the area which is being used as the reservoir rocks. So after the interpretation of this cross section, we basically programmed a drill hole, which is an oriented drill hole, and you can see that this drill hole has worked and basically reached to hot waters in these areas. So this means this interpretation is very useful, and with this cross section we basically reach to the target. This is a section which is east-west to see strike slip faults in the area, which we have no data from the surface, and you can see that borehole data clearly illustrates that there is this much displacement between these two boreholes. Using some of the other data, we basically extrapolated that somewhere in here there must be a strike slip fault which forms a kind of graben structure within the Büyük Menderes graben. Of course, when you make more interpretation of the borehole data, you see that strike slip faults are more than you can think of, and there are beautiful, basically, graben and horse-like structures within the graben itself. To sum up all of this data from the field mapping, from the borehole data, and from the geophysical data, this is what we can say. Well, it's the common knowledge to many structural geologists or those working in Western Turkey. There are three major structures. One of them is the low angle normal faults, okay, which basically controls the exhumation of the metamorphic rocks of the Menderes Massif. There are high angle normal faults like these. These are the normal faults which basically controls the formation of the east-west trending grabens. And on top of them, there are north-south normal faults, this north-south strike slip faults. And we know that intersection and interaction of these normal faults, strike slip faults and detachment faults, are basically localizing the geothermal fluids. And in this diagram, you see that some of those springs in this area basically occurs where the detachment faults are exposed or where the faults intersect. So the faults themselves and the intersection of these faults are used as the major pathways for fluid circulation and geothermal system formation. These north-south trending normal faults are very important because until now we knew that there is faults that exist in the field, but we didn't know that these faults are really present within the graben itself, and they really form major compartments within the graben itself. There are some ideas about the presence of similar grabens within those east-west trending rift basins, I will say, but this is the first time we provide solid evidence about their existing. So these north-south trending strike-slip faults surely cut and displace both detachment fault and high-angle normal faults. They either form by the reactivation of the pre-existing structures. Sometimes they form by the breaching of the relay ramps between the between the normal faults, and they basically result in the compartmentalization of the grabens. Each compartments have different characteristics and basically localize geothermal fluid circulation in some degree, and they become basically suitable reservoir areas, sites for the geothermal exploration. Okay, so the close intersection zones between north-south strike-slip faults, detachment faults, and graben faults must be target areas for future exploration. I think we can basically say that north-south structures control the localization and size and distribution of low resistivity areas, which are easy to recognize from the geophysical data. And these areas can be considered as the potential areas for future target and for future planned boreholes. Because most of these faults have no surface expression at all. The recognition and the geometry of these faults rely solely on the geophysical data. So the quality of the geophysical data, quality of the models, 3D models basically interpreted from these geophysical data are very important. So if you want to really do a better exploration within the grabens, better understanding of these structures is really important. So the basement structures has to be studied well. Of course, in order to have a successful exploration and successful program, the identification, mapping of these strike-slip faults are highly regarded, because until now, our observations clearly shows that the intersection and interaction of these strike-slip faults have a high geothermal capacity, define compartments in the grabens, within the grabens, and these compartments have in some degree, geothermal potential. This is all I can say about the structures of Western Turkey grabens.
Thank you very much, Professor BOZKURT. It's an honor for us having you presenting your research and findings here at the conference. As our next guest, I would like to invite Professor SALIM ETSOURI from Algeria. Professor SALIM?
Yes, I'm here. Thank you, dear Chairman. Hello, everyone. Just a second to share my diaporama. Okay, then do you see the diaporama presentation?
Yes, we can see.
Okay, so first I would like to present myself. I am ETSOURI Salim, doctor in agronomic science from the Department of Rural Engineering of the National Higher School of Agronomy from Algiers and Algeria, and I have the honor to be with you here in the framework of this event, this conference, to present this work entitled The Continental Intercalary in Algeria, Energy Potential and Prospect. To go through the subject, we will start with a short introduction, followed by a synthesis of the knowledge. Then I will present the inventory of its analysis, the different tests, as well as the simulation. Then we will conclude the work. So, energy and water are two essential elements for human beings, and globally, their demands are constantly increasing. The sustained growth of the world population is amplifying this phenomenon. The growing demands of countries for energy security and water resource management have made renewable energy the preferred source of energy in the world. The world's energy production is mainly provided by fossil fuels. The last one are responsible for a great quantity of greenhouse gases emitted in the environment, contributing obviously to the climate changes. Renewable energies, especially those from hydroelectric dams, are actively involved in the preservation of the planet's resources. Considering the many negative environmental and social impacts historically associated with the large dams, one of the solutions for the future of hydroelectricity is a small hydropower. The intercalary continental aquifer is highly coveted for its water as a widely mobilized resource in the northern Sahara. The energy part of this water is completely neglected. Nevertheless, previous studies exist, but have only mentioned the considerable energy that the Albion water table or aquifer releases, called exploitable energy. With this work, we wanted to study this great energy potential and to see the possibilities of exploiting it for agricultural purposes in order to ensure the probable self-sufficiency of neighboring farms in electrical energy. The first part of this work consists in gathering all the informations and making a synthesis of the knowledge around this subject. Like you see in this slide, the aquifer system of the northern Sahara is presented here. The most important aquifer is the intercalary continental, the blue one. It is shared between three countries, Algeria, Tunisia, and Libya. It is good to know that the available data on this system, aquifer system, water use, are based more on estimations than inventories. So this slide presents a west-east longitudinal section of the CI, confined between two impermeable layers with a depth exceeding 1,500 meters. We noticed that there is a very low supply, with about 1 billion meter cube per year, mainly in the foothills of the Sahara Atlas in Algeria. On the other hand, the study conducted by several authors in 2013 shows that the supply of this aquifer is very satisfactory to the point to describing them as a renewable energy or renewable sources. Here we can also see that the CI covers over the half of the Algerian arid zone. For the general characteristics, we can see that the extent in Algeria is about 600,000 kilometers square. The whole volume exceeds 35,000 billion meter cube. The depth to the roof can reach 2,000 meters. The drilling flow reach easily 400 liters per second, and the water have more than 70 degrees Celsius. But the exploitable energy potential of drilling is not studied so far. For the next slide, we see that this aquifer is characterized by its artesianism. The study of the Sahara and Sahel Observatory through exploratory simulation concluded that there would be persistence of artesianism until the year 2038. The condition adopted by the OSS, it means Sahara and Sahel Observatory, under which this calculation was conducted, are as follows. Duration foreseen by the simulation is 40 years, which correspond to the period 1999 to until 2038. And the initial state piezometric situation of the water table or the aquifer at the beginning of the 1999. I want to tell you that you don't have to worry about the years. This is the most recent simulation. For this slide, you can see the region that will keep the artesianism until 2038. For this slide, I wanted to show you a typical drilling in order to be on the same wavelength. As you can see on the top right corner, this drilling is located in the northeast part of Algeria. The drilling station consists of a cooling tower, a drilling head, the piping, obviously, and the safety enclosure with a power supply from the conventional network, the yellow circle that you see here. The Albion drillings are, in most cases, close to transportation routes, farms, and urban areas. This makes them much more functional and accessible. I tried to schematize a drilling as follows. On the right, you can see the drilling head. On the left, the cooling water. The two are interconnected, and the pictures serve to better illustrate the diagram. So what really exists is that we have a drilling which provides hot water at high pressure and flow rate, and discharging its water into tank or used directly while losing all its potential. Of course, we need electrical energy brought from the grid, transformed to supply the cooling fans, requiring 30 kilowatt for the most part. As far as our short-term objective is concerned, at least, we want to integrate turbo generators into the drilling in order to supply electricity to the coolers. And why not inject extra energy into the network while maintaining enough energy for the proper functioning of the drillings. We are therefore well fixed. It is necessary to capture and transform the lost hydraulic energy. As presented in this slide, the share of hydro and renewable energy is increasing, reducing the share of fossil and nuclear fuels to less than 76%. It is important to mention that Algeria doesn't, unfortunately, currently produce energy from hydroelectricity. But I think it is not necessary to present the principal operation of turbo generators or to go through the different type of turbine. Okay, pass. And for the production of the hydroelectricity in the world is done mainly in two ways: hydroelectric dams and small hydroelectric power plants. This last one is declined on several ways: the micro, nano, and pico hydroelectric power plants. The one that is closed to our situation is the micro hydroelectric power plant. Artesianism is a determining character for the outcome of the present work, so it is essential to define the sites considered as suitable for exploitation. In order to identify them, we conduct a survey of the CI drillings operation in Algeria. The essence of this analysis in the survey is presented in this section. So, in this slide, we have been able to synthesize the data collected from the organization presented above, the most important are National Water Resource Agency and the National Office of Irrigation and Drainage. It is a means of collecting all possible information on the Albion drillings and their water. These data are summarized somewhat as follows: identification and location, like code, name, and region, type and execution of drillings, geolocation, energy parameters as flow, pressure, and temperature, and other parameters. As for the general situation, we were able to identify 295 drillings with relatively usable data. We note, however, an irregularity in the collection of data. For example, for flow data, we have only 147 drillings, 19 drillings with temperature data, and none with salinity data. As for the conditions of the drillings, only 65% of the drillings are in working condition as functional drillings. However, we didn't find any correlation between the state of the drillings and their date of completion. Moreover, we can find very old still functional drillings, while others are more recent and not functional. Therefore, we focused our work on the 192 functional drillings. For the energy aspect, we were interested in the parameters flow, pressure, and temperature. As you see, there are 76% of the drillings have flow data. The latter is weakly correlated with the year of completion. The pressure alone is with 37% and the temperature with 10%. The couple flow and pressure is of interest of a calculation of hydraulic power. It represents 1/3 of the drillings we survey. It is interesting to note that only 5% of the drillings have the perfect combination, which is a flow, pressure, and temperature. This reflects a neglect, unfortunately, of the energy aspect during the data collection. The water from the Albion drillings is mainly used for industrial purposes. The supply of drinking water is also ensured by another water aquifer, which explains the low rate of use of the Albion water. Irrigation is concentrated in agricultural areas in the northeast of the aquifer. As for the combined use, it is of a very old nature for a reduced population with agricultural vocation. This inventory is not an update, but it is the first of its kind. So, for these parameters, which means location of the drillings, is what I can say is most of the drillings are located in a place intended for a triple vocation, like industry, irrigation, and population in constant evolution. The region of Wedrir in the northeast of the Northern Sahara is equipped with 78% of the drillings because the land has benefits from the Algerian agricultural revival projects. The date of completion of the drillings tell us something about the longevity of artisanalism. So in the 15th, there was awareness of the vastness of the intercalary continental aquifer. The period from the 70s to the 2000 years, there was a launch of agricultural sectors in the dry lands and the agrarian revolution and nationalization of hydrocarbon on resource, with 41% for industry and 59% for drinking water and irrigation due to urban expansion in southern Algeria. The period after the years 2000 refers a low numbers of drillings carried out mainly due to the consequences of the black insecure period that Algeria suffered. This data can be completed by the drillings with unknown completion dates, as we found a record of 9 drillings not recorded between 2004 and 2008. At this point, criteria for selecting drillings with identifiable energy potential are defined. Drillings currently in operation, we have identified 192 drillings, and drillings with combined flow and pressure data, and drillings with that is not geolocated out, that is not a geolocation outlier. We removed 14 drillings from the table. At the end, we have a total of 133 drillings. For the energetic parameters, and after calculating the power according to the usage, we used the name, the geographical coordinates, and the hydraulic power for all the drillings. In the end, we were able to obtain an annual energy loss exceeding 160 gigawatt hour, corresponding to more than 14,000 ton oil equivalent, or simply more than 100,000 barrels of oil. These figures present a visual on the theoretical hydraulic power of all the drilling sorted by decreasing order. The first observation is we have only one drilling with a potential exceeding 1 megawatt, and we have 7 drillings having a potential more than 500 kilowatt, those representing more than 30% of all the accumulated powers. And we have 51% of the drillings having a potential between 100 and 500 kilowatt. And the drillings with a power lower than 30 kilowatt is not profitable because it is the minimum required for cooling, for example, but remains interesting if coupling is possible. As you see, we can reach almost 500 kilowatt. With this interesting data, we tried to create a map of the power distribution of the ALGEN in Algeria. It is about creating a graphic interface that will help us to better visualize the energetic parameter by having a more precise vision of the distribution of the energetic potential. This data was were entered into GIS software and then processed using the CryGen methods, and the result is there in front of you. Just to situate you a little, it is the eastern zone of the Albion, corresponding to the eastern zone also of the northern Sahara. The areas exceeding 200 kilowatt are almost all located between longitude 5 and 6, with the orientation north-south. This zone have high potential. It is good to notice that it is the same zone that will keep its Artesianism until 2038, according to the simulation. Then we will be able to estimate, I hope, the energy potential of any future drillings. After having clearly identified the exploitable drillings and evaluated their energy potential, we carried out tests under real field conditions using a micro hydropower plant. This section summarizes these experimental tests. So the micro power plant used was graciously made available to us by its owners for research purposes. Thanks a lot for them. This micropower plant can generate a maximum power of 7 kilowatt and provide a maximum flow, and we can use the maximum flow rate of 720 liters per minute. For this part, I have tried to summarize all the tests we have done in the field but we have removed this part of the presentation because it refers to a purely local context. The most interesting thing is to see that the device works properly, and it is obvious. However, we keep in mind these points: the materials and equipment needed for the test, as well as the diameter, are never the same. And the time of visit of the drillings is very limited. After that, the presence of the executive and elected officials of the region, as well as the habitant, seriously disturb the progress of the test. And the extreme climatic conditions and the distance of the drillings from all equipment stores compromise the test. Added to this, the delicate handling of the drilling head requires monitoring and authorizations at several levels. So the implementation of micro hydroelectric power plant upstream of the drilling to transform and exploit the hydraulic energy of the intercalary continental is necessary without social, economic, and environmental restrictions, respecting the sustainable development. Sorry for that. So, since the conditions we faced did not allow for scientifically rigorous testing, we completed this study with a simulation of micro hydropower plant integration using the Red Screen software, which is about a clean energy management software for feasibility analysis of energy efficiency, renewable energy, and cogeneration projects, and for continuous energy performance analysis. More concretely, we used the virtual energy analyzer aspect. For the input data from the virtual energy analyzer to the project model, it is sufficient to enter the location, plant type, technology used, and the project size. For the location data and therefore the climate data, you have just to enter the place or simply locate it on a map, and the software database will be called. In other words, the data will be automatically loaded. For the plant setup, we have to fill in the type of plant and its size in kilowatt for each drilling, for the 133 drillings. For the energy, as hydroelectricity is not a priority given to the lack of water resources that can be used in this sense in Algeria, we have obtained a cost of hydroelectric kilowatt hour. This value is obtained from a direct comparison with the cost of the wind and photovoltaic kilowatt hour price. Don't worry about the currency and the rate. The final estimation at the end of the presentation will be given in US dollars. So resource data such as pressure, flow rate, and other theoretical data must be entered also. For the other parameters that directly or indirectly regulate the energy, it is necessary to define them according to standards, such as, for example, maximum hydraulic losses representing the hydraulic pressure losses in water pipes, generator and turbine efficiency estimated according to a performance curves, turbine availability and turbine type without forgetting the power utilization factor, which is a very important parameter to define and estimated value according to the classified available flows and the different parameters mentioned above. For the cost, we did not break our hands much. We used only the data provided by the Red Screen software. We only need to identify the capital cost and the annual fees. Specifically, we have to define the exact component of capital cost and operation and maintenance cost. For greenhouse gas emissions, we used the average GHG emissions factors for Algeria. For the output, the most relevant results concern the actual electric capacity of the facility, determined from the utilization factor, the electrical energy supplied, the overall investment cost, as well as the annual cost and savings, sales revenue, GHG emissions expressed in ton CO2 per year from the reference power system and the current hydroelectric project, and the gross annual reduction in GHG emission. And all of these for each drilling. Finally, we found the available power about 14 megawatt instead of 19 megawatt calculated power. In the same way, the available energy is about 125 gigawatt hour per year instead of 168 gigawatt per year calculated from the calculated energy. As you know, losses as well as yields play an important role in the dimensioning of hydroelectric installation. In the other hand, equip all the identified drillings with micro hydropower plants give us an annual income of more than $7 billion US. But the energy from the Albion drillings is dissipated at the surface. It is therefore not yet exploited, and then no income, and it is on all the Albion aquifer. I mean the three countries, Algeria, Tunisia, and Libya. For this slide, the gross annual reduction of GHG emission is around 93%. This significant difference is justified by the fact that the national electricity production is essentially based on fossil fuels that generate significant quantities of GHG. So this 70,000 of ton CO2 is a significant amount of GHG not emitted to the environment, corresponding to more than 160,000 oil barrels, or if you want another comparison, about 30 million liters of gasoline. All of these not consumed annually. The drillings are not all in the same area, and it is inconceivable that to physically link the production of several distant drillings. To think either by individual drillings or by very close system, grouping very close drillings forming a unit around a village or several farms in order to develop the exploitation of the supplied electricity. On this slide, I show you some operations related to agriculture that require energy at different level. For example, for the cooling of water from the Albion drillings, from 80 degrees to 35 degrees, we need a cooling tower functioning with a 30 kilowatt engine. For the farm, for the second example, for the farm irrigation, we have a very large land with increased expense, and the pivot irrigation system, it is the usually used system in these conditions, is energy consuming and time consuming with unavoidable rush hour of use. For the last example, is for amenities of nearby farms that need light, ventilation, fresh water, different agricultural transformation processes, and personal convenience. The energy supplied by the drilling water may be sufficient to offset a large part of these needs. For conclusion, we just need to remind the facts. We have at the beginning, in the two situations, water and energy in the first case the energy is lost, but the water is used for different purpose by injecting energy from outside. In the second case, the energy is recovered, used to provide for immediate needs. It can also be injected into a state or a private grid. So I will end my speech with some important points. Update the state of knowledge around the CI is important. We have to enhance the value of the CI aquifer by exploiting its energy potential, and the use of simulation software for the integration of micro hydropower plants is an important tool for the development of energy projects. It will be interesting to create a commercial entity whose objectives would be the technical and financial management of the hydroelectric production from the Albion drillings in the 3 countries without promoting the consumption of this very precious water. So with that, I thank you for your attention, and I will return the floor to you.
Thank you very much for your valuable contributions, Dr. ETSOURI. We are very pleased to have you here with us. In the last session of Day 3 presentations, we have hosted 3 very valuable scientists. I express my sincerest gratitude to them for being with us. Thank you very much, professors. I would also like to thank all the professors who have joined and honored us today. This is the end of Day 3 on NRSEM 2021. Hope to meeting you tomorrow. Until then, I wish you all good health and well-being. Goodbye.
Catching a bus, never nothing when it's really done.